Right, the onset of blood lactate accumulation, OBLA, is where we start to have a significant amount of blood lactate accumulation versus lactate threshold is where we just start to accumulate blood lactate, where we're not able to metabolize it and or oxidize it and use it for energy, that it starts accumulating. Whereas the OBLA is where we significantly have an accumulation. And so if we train at either the lactate threshold or the OBLA, it will raise these thresholds or it will allow us to maintain aerobic energy production longer before we start to accumulate the lactate. And this is usually due to an increased oxidative capacity to produce energy in the muscle, and that's by increasing mitochondria, which is where oxidative energy production occurs. And there's more enzymes, and there's a greater delivery of oxygen from the with myoglobin from the capillaries to the mitochondria. And this is what the lactate threshold looks like. And as you can see, the yellow and untrained individual, they have at a lower percentage of their VO2 max, they have their lactate threshold. So as they raise their intensity of effort and they get up to about 50% of their max, that's when they start to accumulate lactate. Whereas a trained athlete, they can maintain a greater percentage of their VO2 max. This individual in the green is out to 75% before they start to accumulate lactate. So the oxidative or the aerobic energy system is just where we produce oxygen or ATP in the presence of oxygen. And the oxidative system fuels our exercise or fuels our body's needs for ATP at rest and with submaximal aerobic types of activities. And they will use primarily carbohydrates, glucose or glycogen, as well as fats. The fats are used at lower intensities for energy substrates, and protein is rarely used. It's usually if it's an extended bout of exercise or a person's in a low energy state. We call oxidative energy production cellular respiration because it is using oxygen. Oxygen is present as we produce ATP. It takes place in the mitochondria, which are specialized organelles in the muscle cell, and we actually increase the number of mitochondria as we do aerobic training. And the oxidative energy production produces more ATP than is produced in the glycolytic system. And the oxidative system actually involves multiple steps, and always the first step is glycolysis, because glycolysis that we talked about before produces pyruvic acid, but if oxygen is present, pyruvic acid can be converted to acetyl coenzyme A rather than lactic acid, and it will be transported to the mitochondria to be used for energy production. As well, in the mitochondria, then acetyl-CoA goes through the Krebs cycle. It produces ATP. Also, hydrogen ions are released, and the hydrogen ions then go to the electron transport chain to synthesize ATP as a form of energy to produce even more ATP. So there's the three steps: the glycolysis, which produces the pyruvic acid, which then is converted to acetyl coenzyme A and taken to the mitochondria, which then enters the Krebs cycle to produce ATP and hydrogen ions. Hydrogen ions then go to the electron transport chain to produce even more ATP. This we've already looked at, the glycolysis, and I already spoke about. And here's the Krebs cycle. The hydrogen ions are transported by what's called NAD and FAD, and once the hydrogen ions are produced in the Krebs cycles, They bind with NAD and FAD, and they will transport that then to the electron transport chain for ATP production. So in the electron transport chain, that's where we take ADP and we add a phosphate group and produce energy to form ATP. And so this is what the oxidative system looks like. Starts out first with glycolysis, resulting in pyruvic acid production, which is converted to acetyl coenzyme A, which then enters the Krebs cycle. There is some ATP produced in the Krebs cycle, but also you can see the hydrogen ions are produced. Carbon dioxide is also produced, and then it goes from there. The hydrogen ions then go to the electron transport chain to produce energy, which then allows us to resynthesize ATP. And when we use fat as our energy source, what we break down triglycerides into free fatty acids. They enter the mitochondria in this oxidative process, and we call this beta oxidation. And there's much greater energy production, ATP production, when we use fat as our substrate in the oxidative system. And protein, as I've mentioned before, protein can be converted either to glucose or free fatty acids. When we convert it to glucose, we call this gluconeogenesis. And this just gives you an idea of how much ATP is produced when we use glucose as our substrate in the oxidative system. We produce 38 ATP. When we use stored glucose, which is glycogen, we produce 39 ATP. But when we oxidize fat, you can see we have a much greater energy production. And as athletes train, they increase their oxidative enzymes. They train their slow twitch fibers to be more, to increase the oxidative capacity of the slow twitch fibers. This we might have some conversion of some of those fast twitch fibers as well to increase their oxidative capacity. So all of this adds up to increasing the abilities muscle to produce, when we train aerobically, to produce energy oxidatively, and allows that individual to fuel their exercise intensities through oxidative energy production and postpone the accumulation of lactate. And this just, let me go back here. Let's see, how do I go back? This just shows there's an overlap. All the systems are always working. It's just that one is more dominant than the other. So immediately when we exercise, we're relying on the phosphagen system, stored ATP and creatine phosphate in the muscle, but it's very limited supply. And then we go to our anaerobic glycolysis, which we have glucose available and stored glycogen, but we also have this process if we convert our pyruvate to lactate eventually. As the intensity increases, we can't maintain that type of energy production because of the accumulation of lactate. And our long-term energy system is our oxidative, with fat being our most greatest energy production. And so that's a great source of energy, because if we maintain exercise at a low enough intensity, we can metabolize the fat, and we have unlimited supply of fat. And so it's not just a start and stop of each system. When we start exercising, all systems start, but they just, at the very beginning, we quickly meet our energy demands with the phosphagen system, and but that quickly depletes. And by the time that depletes, the anaerobic glycolysis system is up and running and able to produce ATP. But then as that starts to diminish, the oxidative energy system. We've been had time to deliver oxygen to the working muscle, and so then the oxidative system will kick in if it's at a low enough intensity. And this just shows just a ranking of how quickly they produce ATP. Okay, and you can see there at the bottom the fat, using fat oxidatively is the slowest at producing ATP. And that's why when we do aerobic or oxidative energy production and we increase our intensity to a certain point, we're not able to, the system's not fast enough to produce ATP with fat, and we shift over again to using glucose or glycogen. And then it just shows just the opposite, how much ATP is produced with fat being rated number 1 and the phosphagen system producing the least amount of ATP. And this also gives you some idea of the dominant energy system at different points in time. And why some athletes experience fatigue, they can deplete their creatine phosphate, and so they can't quickly synthesize ATP, or they might have depleted their muscle glycogen. And if you're exercising, even if you're exercising aerobically, and you're using your glycogen, you can deplete your muscle glycogen stores with higher intensity effort. So running a marathon, when they hit the wall, that sensation, and they have to cut down their intensity, that's because they've depleted their muscle glycogen, and they have to decrease their intensity so they can use fat as their source for oxidative energy production.